morning to everybody. In this video, I am going to discussing about special diodes. There are different types of special diode. One is Zener diode. In Zener diode, we are going to discuss about breakdown mechanisms and Zener diode applications. What are the applications of Zener diode? We are also discussing in this unit. And LED and photodiode, tunnel diode, SCR and UJT. We are going to discuss in this unit. Now let us discuss one by one. Zener diode is a special design diode. It is used to dissipate power in breakdown region. It is heavily doped diode. Here we are using doping materials heavily to design P and N type materials. It is also a combination of P type material and N type material. Here we are taking intrinsic material. One part is doped with P type material and another part is doped with N type material like ordinary PN junction diode. But here we are using doping concentration is more. It is also known as breakdown diode because it operates in reverse bias also. Basically, the Zener diode is operate in reverse bias. Due to this application, it is used as a Zener voltage regulator. In forward bias, it acts as a general purpose PN junction diode. But in reverse bias also, it allows flow of current. That's why it is also known as backward current or backward diode or breakdown diode. This is the logic symbol of PN junction diode, and this is the normally available Zener diode. The VI characteristics at the operation of the Zener diode is, while it is connecting in forward bias, it acts as normal diode. That means the positive terminal of the battery is connected to P type and negative terminal of the battery is connected to N type. Then we will provide forward bias. In forward bias condition, after cut-in voltage, it allows flow of current maximum. So the cut-in voltages for germanium is 0.3 volts and for silicon is 0.7 volts. Once it reaches cut-in voltages, it allows maximum flow of current. In forward bias, the resistance is low and current is maximum. In reverse bias, there is a voltage. That voltage is known as breakdown voltage. Once the device reaches that breakdown voltage, then the device goes into Zener breakdown. So once the device goes into breakdown region, it maintains constant output irrespective of any input variations. So this is the characteristics of VI characteristics of PN junction diode. We will get these characteristics in forward bias as well as in reverse bias. The operation of Zener diode involves two mechanisms. One is avalanche breakdown and another one is Zener breakdown. Let us discuss one by one briefly. What is meant by avalanche breakdown? The avalanche breakdown occurs because of the electrons collision inside the PN junction. That means when we apply reverse voltage, the minority charge carriers are move away from the minority charge carriers in P type is electrons. These electrons are repelled by the negative terminal of the battery towards the junction, and the minority carriers in N type is holes. These holes are repelled by the positive terminal of the battery towards the junction. So they moving towards the junction, they will collide with each other. At the collision, they will form a recombination electron hole pair. So due to this recombination, there is a current flow. That current flow is known as current flow in the avalanche breakdown region. So avalanche breakdown occurs due to collision of electrons inside the PN junction. This avalanche breakdown generally available occurs in low doping material. That means we are adding low impurities to that material, then avalanche breakdown will occur. Avalanche breakdown has positive temperature coefficient. That means if the temperature increases, the value of the resistance also increases. That is called temperature coefficient. What is positive temperature coefficient? Another one is Zener breakdown. It occurs in heavily doped material and it is occurs due to because of the applying electric field across the junction. High doping material means we are adding more impurities. We are adding concentration of more impurities to PN junction at that material. Then we will get the high doping material. So in high doping material, there is a breakdown occurs. That breakdown is known as Zener breakdown. Here in Zener breakdown, the temperature coefficient is negative. Here the temperature is increases, the value of resistance is decreases. So the temperature is inversely proportional to the resistance. That's why the temperature coefficient is negative. In the Zener breakdown, ionization occurs because of the electric field. That means recombination occurs. Recombination of charge carriers occurs due to electric field. But in avalanche breakdown, recombination occurs due to flow of electrons. So these two mechanisms occurs in the PN junction diode. One mechanism, if you observe the VI characteristics of PN junction diode, before the VZ, that means Zener voltage, the breakdown occurs is known as avalanche breakdown. After VZ, the breakdown occurs is known as Zener breakdown. So VZ is generally the Zener diode voltage. VZ is 6 volts. If the VZ is less than 6 volts, the breakdown occurs is avalanche breakdown. If VZ is greater than 6 volts, the breakdown occurs is Zener breakdown. Zener resistance and diode ratings. There are two types of Zener resistances. One is DCR static resistance and another one is ACR dynamic resistance. Here, let us discuss one by one briefly. DCR static resistance. The ratio of total Zener voltage to total current at a given operating point is known as DCR static resistance. That means no AC voltage is applied. At that time, we are getting the voltage and current. That ratio of that voltage and current is known as the DC or static resistance. So RZ equal the DCR static resistance is represented with RZ. So RZ equal to VZQ by IZQ. Here Q means operating point. This is the symbol of Zener diode, and the second one, this one is the equivalent circuit of Zener diode. Here we are connecting resistance in series with the Zener diode because to avoid the Zener diode excess flow of current through the Zener diode, we are connecting resistance in series with Zener diode. ACR dynamic resistance RZ maximum. It is difference in voltage divided by current difference, that is change in voltage by change in current. So at the zero conditions we will get some voltage and current. After applying signal to the Zener diode, we will get another values. So the difference in starting value and after applying signal we will get some value. The difference in both the values is known as the difference in change in voltage to change in current is called ACR dynamic resistance. It is represented RZ maximum. If RZ is less, then the Zener diode will be better as a voltage regulator. If the RS is less, the voltage regulator is poor. Zener diode rating. Minimum Zener current is represented with IZ minimum. It is the minimum reverse saturation current where the device goes into breakdown region. In that reverse current, the device goes into stable state. So that current is known as minimum Zener current, that is represented with IZ minimum. And one more current is maximum Zener current. It is represented with IZ maximum related to power rating. So here the power is represented with PZ maximum. Why we are considering Z every time is here we are considering the Zener diode, that's why we are saying PZ maximum. So IZ maximum equal to PZ maximum by VZ. We know the equation for P equal to V into I. So from that relation we are getting IZ maximum equal to PZ maximum by VZ. Maximum power of Zener diode, that is represented with PZ. It is the power dissipation of the Zener diode. It equals to the product of Zener voltage and Zener current. So PZ equal to VZ into IZ. Effect of Zener diode on temperature. Here the temperature, we have to learn or we have to know one term, that is temperature coefficient represented with Tc. That what is meant by temperature coefficient? The percentage change in the Zener voltage for every degree centigrade change in temperature is called temperature coefficient. In normal PN junction diode, the temperature coefficient is considered with current, but in Zener diode, the temperature change in temperature coefficient with respect to the Zener voltage. So if Vz is less than 6 volts, then the temperature coefficient is negative. If Vz, that means Zener voltage is greater than 6 volts, then temperature coefficient is positive. That means temperature coefficient is positive means if the temperature is increases, the resistance also increases. The temperature coefficient is negative means if the temperature is increases, the resistance value is decreases. So for Vz less than 6 volts, the temperature coefficient is negative. For Vz greater than 6 volts, the temperature coefficient is positive. Applications of Zener diode. The main application of Zener diode is voltage regulator. Here, irrespective of input variations, it maintains constant output. The second one is Zener comparator. It compares two Zener voltages and gives the best result. In that application, we are using Zener diode as a Zener comparator. And third one is Zener limiter. So it takes the wanted voltage and remove the limit the remaining voltage. For that application, we are using Zener diode as a Zener limiter. We can also use Zener diode in power supplies also. That means to provide that it can be used as a regulator in power supplies. The output of regulator is gives constant output irrespective of input variations or load variations. Zener diode as a voltage regulator. A voltage regulator is an electronic device that provides stable DC output, not AC output. It provides stable DC output independent of load variation. If there is a change in load current, but the output can't be changed. If there is a change in the temperature, but the output voltage doesn't change. And if there is a change in line voltage variations, but there is no change in the output voltage. So for that, irrespective of these variations, it maintains a constant output. So that's why we are using Zener diode as a voltage regulator. Here Zener voltage is an electronic device. In that voltage regulator, we are using Zener diode. Factors determining the stability. So, to maintain a stability, what are the factors influencing? The first one is input unregulated DC voltage, VN. That means unregulated means pulsating DC is given as the input. So from this we are providing unregulated input into regulated output at the output. So at the input we are giving unregulated DC voltage, at the output we are getting regulated output, DC output. So this is also affecting the stability of the voltage regulator. And one more is load current. If there is a change in the load current but there is no change in the output voltage. So one more is temperature. If generally in PN junction diode, if temperature is increases, current is also increases. According to current, voltage will also increases. But in Zener diode, if there is a change in the temperature but there is no change in the output voltage, that these are the factors affecting or determining the stability of the voltage regulator. Line regulation. Here, line regulation is change in output voltage to change in input voltage. That means delta V naught by delta V in is the line regulation. And one more is load regulation. The formula for percentage load regulation is V no load minus V full load by V no load. For percentage, we should multiply the equation with 100. Or one more equation for load regulation is V no load minus V full load by full load into 100. Where we are getting no load voltages and full load voltage. Before no voltage is applied to that means no load is connected to the Zener voltage regulator. At that time we are getting voltage. That voltage is known as V no load voltage. After connecting load voltage to the voltage regulator, then we are getting the voltage. That voltage is known as the full load voltage. So percentage load regulation. Here after giving the load, how much of regulation it provides is known as the load regulation. So percentage load regulation equal to V no load minus V full load by V full load into 100 or V no load minus V full load by V no load into 100. This is the percentage load regulation. Zener diode as a voltage regulator. So this is the circuit diagram of the Zener diode as a voltage regulator. Here we are taking Zener diode and we are connecting resistance in series with the Zener diode. The Zener diode is operates in reverse bias. That's why the cathode is connected to the positive terminal of the battery and the anode is connected to the negative terminal of the battery. So by this connection we are providing reverse bias to the Zener diode. And we are connecting load resistor RL across the Zener diode. Across the load resistor we are taking output voltage that is represented with Vz. So this is the circuit diagram of the Zener diode as a voltage regulator. So these are the VI characteristics of Zener diode as a voltage regulator. Here also we are taking forward characteristics and reverse characteristics. We are drawing forward characteristics between forward voltage Vf and forward current If. For reverse in forward bias condition, the Zener diode acts as a normal diode. So until the cut-in voltage, it doesn't allow any flow of current. After it reaches the cut-in voltage, that means 0.3 volts for germanium and 0.37 volts for silicon, it allows the maximum flow of current in forward bias. In reverse bias conditions, we are taking reverse current on y-axis in milliamps and reverse voltage in volts on x-axis. So, until the knee voltage or Zener voltage, the current flows due to minority charge carriers. Once the Zener diode enters into until the region is known as avalanche region. Once the Zener diode reaches Zener voltage, that is represented with Vz. Generally, here the Zener voltage is 6 volts. So, if the Zener voltage is greater than 6 volts, the device goes into Zener breakdown region. At that time, maximum current flows into the reverse current. Maximum reverse current flows into the device. So, that region is called Zener region. Irrespective of any input variations, that means load variations or load resistance variations and load current variations or input variations, but the output is maintaining constant. That means the output maintains at 6 volts only. There is no change in the voltage after once it reaching the Zener voltage. So these are the VI characteristics of the Zener diode as a voltage regulator. Thank you.